related to optimization of soft switching converters utilizing wide bandgap semiconductors. Before I get started, I'd like to give credit where credit is due. A lot of the work that you're going to see today is due to the efforts of my PhD student, Ali Shahabi, who has been working with me for a couple of years and has become a veritable expert in this subject matter. So I'm presenting today much of his work. So here's a quick overview of what I plan to talk about today. I'm going to give you first a brief introduction and motivation for the work. Then we're going to dive into the details of a particular topology that I've selected as a case study to demonstrate some of the concepts that we need to understand for the topic at hand, and that topology is the phase-shifted full bridge. We'll do a little bit of modeling of this topology. Then I'll talk briefly about a prototype converter that we've fabricated. Then I want to spend a couple of minutes talking about some metrology issues that really can make you or break you when it comes to understanding the efficiency, the experimental efficiency of your system. Then briefly go over some model validation and some efficiency trends that we've been able to ascertain. And then talk about some future research that we're just kind of embarking on now related to using a genetic algorithm for further optimization of this topology. So to begin with, as far as a kind of introduction or motivation goes, I'd like to mention, and as we're all very aware that with the advent of wide bandgap semiconductors, we have the opportunity to make great strides in the performance of converters based on this technology. We are seeing, of course, increased emphasis on achieving unprecedented levels of performance in terms of both efficiency and power density. However, one of the key things that goes along with this is we really have to operate at elevated switching frequencies in order to really move the needle when it comes to power density, which is kind of we take as a given. But then one side effect of that is that as we achieve higher frequency, of course, we accumulate additional switching losses when we make that design decision, which has a negative effect on our system efficiency. So, as with most things, there's a trade-off here that we must manage. So, kind of to come to the end of that logical process, if we want to simultaneously achieve both high efficiency and high power density, we need some method to mitigate switching losses so that we can use high efficiency to get our power density and then not incur the penalty of higher switching in terms of efficiency. And the well-recognized solution to this is one of several soft switching techniques. So to give you just a little bit of background for those of you who aren't familiar, the difference between hard switching and soft switching. During hard switching, we have substantial overlap between the voltage across our device and the current through, which results in substantial instantaneous power loss during our switching transitions. And this is a key component of our switching, of our frequency-dependent losses in the system. There are, of course, other frequency-dependent losses such as core loss in our magnetics and a few ancillary other frequency-dependent loss mechanisms. But I would argue that the preeminent frequency-dependent loss mechanism is the switching loss of your semiconductors. So the primary contributor to this is the discharge of the output capacitance through the device channel during the turn on of the switch. And if we have some mechanism by which we can delay the rise of the current such that this overlap between the voltage and current becomes minimal or negligible, this is a means by which we can effectively eliminate this turn-on loss through a process called zero voltage switching. All right, so just a general description here of ZBS. In order to achieve this reduction of overlap, we need, typically the way this is done is through the use of some resonant action. So we use a resonant process to relocate the voltage across the switch prior to turn on. Conventionally, this is done through an LC resonance that's contributed by the inductive elements in the power stage. This may include the leakage inductance of your transformer primary, for example, and you may also need an ancillary inductor to make up enough energy storage to achieve these transitions. And then the other part of the resonant tank is the intrinsic capacitance of the switches, usually the output capacitance being the dominant component. So this allows us to achieve zero voltage switching, as I'm showing here in this little graphic. If I can get my pointer to turn on. As long as we reduce the drain to source voltage for the switch that's turning on prior to gating it on, then we have an opportunity to achieve ZVS. All right, so however, one challenge here is that the likelihood of achieving ZVS is a function of many parameters in our circuit. We have our semiconductor device characteristics play into this, as well as the amount of inductance in our primary side. Also, the dead times play a strong role in determining whether or not we'll achieve soft switching, as well as the output power level of our converter. And one challenge is that often we don't know whether we're going to achieve ZVS for a given set of conditions until we actually build the converter and operate it on the bench. And oftentimes, the design of this type of converter requires substantial bench-level tuning in order to achieve soft switching across a large range of load power values. So this is kind of certainly non-optimal because it's kind of a seat-of-the-pants optimization process that oftentimes you're left wondering if there's performance left on the table that you weren't able to capture. So in order to do better than this, we need some form of model. So now I'm going to talk a little bit about, for this selected topology, again, which is representative of a larger set of topologies that can achieve soft switching, but this is one important example topology. So we'll talk a little bit about a model. Before we do, just to give you a little bit of introduction for those of you who are not familiar with this topology, on our primary side we have 4 primary side switches, Q1 through Q4. In this example, I'm showing our transformer and then a passive rectification on the secondary. In this topology, one unique thing is that all switches operate with about a 50% duty cycle. And the amount of power transfer is determined not by the duty cycle of the individual switch, but due to the amount of overlap between the conduction time of the diagonal switch pairs. And an important piece of terminology here that we need to understand, if we consider Q1 and Q4 to be one pair of diagonal switches and Q2, Q3 to be the other pair, then we need to identify within each of those pairs the switch that initiates the switching sequence. So for Q1 and Q4, we see that Q4 always switches before Q1, and for that reason we call it a leading switch. Similarly, for the Q2, Q3 pair, we see that Q3 always gates on before Q2, always gates on before Q3, which is why it is referred to as a leading switch. The other two, Q1 and Q3, are referred to as lagging switches. And again, I'm showing them here with leading on the right side, lagging on the left. That's just a convention. It's really the leading versus lagging is determined by your gating sequence, not by the position in the circuit. However, this distinction is important because the leading and lagging switches have different characteristics in this topology. So what are some of the parameters that we must adjust or tune in order to achieve ZBS in this topology. So the three main categories of tuning parameters are the dead times for the leading and lagging switch pairs, which, as we'll see in a moment, are going to be different. Also, the resonant inductor plays a major role in determining whether or not we achieve ZBS for a given power level. And the output capacitance of our switches also plays a role. All right, so quick note on realization of ZBS. So here, this is a experimental waveform that was captured for our prototype converter, but annotated so that we can understand the opportunity for ZBS. So what we have here is a resonant induced transition, wherein which we have the drain to source voltage for the switch that's about to turn on is dropped from the DC link voltage, which in this case is 750 volts, down to 0. And this occurs during this, what I've annotated here as T-min. So this is the minimum amount of time that we must wait before gating on the switch if we want to achieve 0 voltage switching. However, if we wait too long, we'll find that since, again, this is a resonant behavior, the drain to source voltage will actually ring back up to the bus. And so in addition to a minimum dead time, there's also a maximum time that we can wait if we want to achieve ZBS. So what this indicates is that there's a window of opportunity during which we can gate on the switch in order to achieve ZBS. And this window of opportunity is bounded on both the minimum and maximum sides. So we have to be very careful with our selection of bed time in order to achieve ZBS. So this is this is an important indicator that we don't just need to guess at this, we need some model to help us identify when we should make these dead time selections. All right, so thus we have been working on a model of this topology, and it turns out that if we take this rather complex topology and break it down and define an equivalent circuit for the period of time during which the individual switch pairs are going to turn on, then we can not only estimate, but we can very precisely predict the minimum and maximum dead times allowable to achieve ZBS. And so I've shown here we have an equivalent circuit for the lagging switch ZBS, and directly from this equivalent circuit, we can identify the following minimum and maximum dead times. There's a good bit that goes into this derivation, and it is detailed in this paper that's referenced down here at the bottom. This has been submitted to the special issue on wide bandgap devices and applications for the Journal of Emerging and Selected Topics in Power Electronics, which has been provisionally accepted to that special issue. So you should be able to read about it shortly. But in any case, this is the model that we've come up with for the lagging switches. And then in the case of the leading switches, we have a slightly more complex equivalent circuit. For this case, it's actually pretty complex to determine a closed form solution for the min and max dead times. But we can pretty readily come up with an S-domain expression for the switch voltage, which we've done. And then we can numerically solve this expression for the min and max dead times. I've omitted the definitions of the coefficients here as they're pretty involved, but again, all of that detail is in this paper. Once we define this model, we can then do some very interesting analysis. And on the next slide, I'm showing we can do some parametric studies. We can look at, as a function of the dead time values and as a function of the output power, which are shown here on the Y and X axes respectively. We can kind of draw some boundaries around the conditions under which we expect to achieve ZBS. And then we can sweep parameters. So on the left here, I'm showing the, as we change the resonant inductor value, as we make it larger, we see that the model predicts the boundaries of min and max dead time will grow. So if we have a larger resonant inductor, we have a more generous time frame during which we can switch the device on to achieve ZVS. And then the influence of the switch capacitance also plays a role. One important thing is as we increase the COSS of the switch for a given set of conditions, we find that we can only achieve ZVS down to a particular output power. So for example, if we had a 4.2 times higher COSS than kind of our baseline setup, we can only achieve ZVS down to about 3.5 kilowatts, whereas the standard kind of conventional setup would get us ZVS down to 1 kilowatt. So that implies that the device characteristics actually play a very important role in determining the likelihood of ZVS for a given set of circuit values. We can do a similar thing for the leading switch. We find in the case of the leading switches that the opportunity for ZVS is much more generous. So specifically, we find that there's essentially no maximum dead time for the leading switches. And this is well known from the literature. It's known that the leading switches are much easier to achieve ZVS. Part of that has to do with the fact that we have the reflected load current assisting in the ZVS transition. But in any case, we find that the sensitivity to the resonant inductor value is essentially negligible for the leading switches. However, the output capacitance of the devices does still play a role. Let me see if I can. Okay. So with that understood, with our model kind of defined, next we're going to start looking at how we can validate this model and then what we can learn as a consequence of that. But before I do that, I'd like to spend just a few moments talking about the converter prototype itself and then some metrology considerations before we get into the empirical results. So as part of this work, we designed and implemented a 10 kilowatt phase shifted full bridge converter that's shown here. I have a 3D CAD rendering and then our operational prototype. This was kind of notionally designed after a new data center architecture that relies on a 480 volt three-phase pseudo-regulated or passively rectified and pseudo-regulated 750 volt bus, excuse me, that needs to be converted to 350 volts DC for distribution throughout a server cabinet. So that defined the input and output voltage levels shown here. We're operating this particular converter at 100 kilohertz, and we get a peak efficiency of about 97%. The power density of this is around 40 watts per cubic inch. This was not initially designed for maximum power density, but to make it easy to instrument and characterize the system. And so we're actually working on an optimized version now after kind of learning a lot about the trends and characteristics of this topology. We're now doing a redesign of this structure, which should achieve about a 2x increase in power density. In any case, we have published some papers on this work. This was our APEC paper from 2018 that kind of detailed the design particulars. A few details about the converter. We're using 1200 volt silicon carbide MOSFETs, a total of 4 on the primary side. On the secondary side, we currently have passive rectification with 1200 volt 20 amp silicon carbide Schottkys. We have a total of 8 secondary rectifiers in this implementation. A few details on the circuit design. We designed a custom gate drive module with high DVDT immunity. And this is some aspects of this design were based on a paper that was published in 2015 by Xuning Zhang that allows that has provisions for steering common mode current around the sensitive digital isolator input to avoid false triggering due to common mode noise. that was a key aspect of our system being robust and resilient. So that's an important finding, and that's a great paper to reference when you're if you're struggling with common mode noise immunity. On the transformer side, we had a custom designed planar transformer designed and fabricated for us by Peyton Planar. This is we had to go through a couple iterations on this, but we have a really nice, robust thermal design in the current implementation. Next, we have kind of a unique thermal management design. We implemented a what we call our heatsink rail. It's an internal fin heatsink from a German company. This is an aluminum extrusion with internal fins, and we have this kind of central heatsink mounted in the midst of the converter, and we have all power semiconductors mounted to this. And then we have a centrifugal blower that forces air through this cooling channel. And some of the benefits of this design is it provides a measure of thermal averaging, such that if some of the semiconductors are hotter than others, we kind of get some amount of thermal balancing, which helps us to mitigate the risk of thermal runaway. Another advantage is that we can easily convert this to liquid cooling simply by sealing the ends of the tube and hooking up a chiller instead of forced air. All right, some thermal pictures of the system during operation. The main thing to point out here is that this is operation at 10 kilowatts output power. And in this configuration, we see that the silicon carbide MOSFETs are not even getting hot at all. We see our primary side MOSFETs are at 53 and 48 degrees. We see a little bit more thermal stress on our magnetics, our output inductor, and our resonant inductor. And then our secondary diodes are the hottest of all in this particular configuration. All right, so now let me give you just a couple of moments on metrology considerations, and then we'll jump into some of our experimental results. So this is a picture of our test bench in my lab at Alabama. I have here our converter on the bench. We have our power quality analyzer, resistive load bank here underneath. I have our input supply over here on the left. And wanted to talk for a moment about the instrumentation that's used. The initial configuration that we used for measuring efficiency was we had implemented our power quality analyzer with Hall effect sensors for the input and output current. These are very convenient because you can just slip them around your input and output conductors to measure current. However, we found throughout the course of this evaluation that these current sensors, like really all such sensors, have small offsets, and what we found here is that when we are trying to quantify the efficiency of this converter, these small offsets can lead to substantial error in our efficiency computation. So for example, showing here at 9.75 kilowatts, a 350 watt loss, measured loss, if we have an actual current of 13 amps, but the sensor has a 100 milliamp offset, that will give us an inaccuracy in the power measurement of about 75 watts. So what we determined was that the resolution and accuracy of these current sensors were insufficient for accurately quantifying the characteristics of this converter. So what we ended up doing was we swapped to shunts. So our PQA that we're using in this instance has internal shunts. It actually has two different shunts. One that is kind of a high resolution but limited dynamic range that can only go to 1 amp, and then it has a second current shunt that can withstand up to 30 amps. And we found that this approach, while a little bit less convenient because you have to run both your input and output through the PQA, kind of where the PQA is in series with both the input and output of the converter. Nevertheless, this gives you a far better, accurate estimate of the efficiency. One other thing that we need to be aware of is that when tracking efficiency of this type of converter, it's not sufficient just to take a snapshot. And what I'm showing here is an efficiency capture over the first 15 minutes of operation of this converter. And what we see is that as our system kind of settles in thermally, we see some substantial variation in the efficiency. We also have some kind of variation around the central tendency, but in any case, it's important. What we found is it's very important to let your converter kind of settle in thermally before capturing the efficiency, and when you do so, to actually do some averaging in order to kind of mitigate the measurement noise, which is always going to be present to some degree or another. So those are some of the main takeaways from the metrology that we found going throughout this through this evaluation. So now let's talk a little bit about some empirical results. So I'll briefly show you validation of our model as well as some efficiency trends. So first off, one of the things that we did is during this evaluation, we tested a bunch of different configurations of resonant inductor. We modified the output capacitance of the switches by adding additional linear capacitance across drain source to kind of validate our model trends. And then what we did to validate the dead time predictions was we set the dead time in the actual converter to a very large value, and we measured the min and max dead times from monitoring the drain to source voltage across the switch. And then we plot these contours as I showed previously. An example here, the shaded area is the region within which we expect to achieve ZVS. And then the asterisks in all cases are going to show the experimentally verified min and max dead times. So of course, these would be the maximum dead times for this example, and these would be the minimum dead times. All right, so I'm going to kind of tab through some examples here. So this is with a resonant inductor. So this is for the lagging switch pair. And so as a function of output power, we can ascertain the minimum and maximum dead times as we step the resonant inductor value. And so again, the asterisks here represent the measured values, and the shaded boundary is what our model predicts. And so we see that as we toggle through different resonant inductor values, we have very good agreement between what the model predicts and the min and max dead times that were measured in experiments. So I'll just toggle through those one more time. All right, and next is the output capacitance. So again, this is for the lagging switch pair. So with the kind of normal 80 milliohm silicon carbide MOSFET output capacitance, this is the model prediction and empirical validation. And as we kind of stack additional capacitance in parallel, we see that the boundary region kind of moves up and to the right, and then that's what we get with about 4x the nominal value. So I'll tab through those one more time. And again, the asterisks represent the experimentally measured min and max dead times. All right, now switching over to the leading switch. And here again, what we find with the leading switch pair is that there is no maximum dead time. It's strictly a function of the minimum dead time. And again, the resonant inductor is not a sensitive parameter for the leading switch ZVS. It's really more a function of the COSS. And what we see is that as we bulk up COSS, the minimum dead time increases, and particularly it increases at light load. So that's, again, tapping through these a couple times. So in all cases, what we see is that our theoretical model that we derived very accurately predicts the dead time requirements for achieving ZVS. All right, now let's take a look at the efficiency. So in addition to sweeping the parameters that influence the min and max dead times, we did a range of experimental measurements where we mapped out the efficiency that was measured as a function, again, of output power and dead time. And I should mention that in this case, the leading and lagging dead times were set to the same value that in all cases. So I'm going to show you the efficiency contours as we sweep the resonant inductor value from 5 mic to 20 mic. So what we see is that the dark red regions, which is the highest efficiency, it gets larger as the resonant inductor gets larger. I should also point out that we're overlaying here the regions of ZVS on this parametric map, such that what we expect is that when both switch pairs achieve ZVS, we should see the highest efficiency. And in fact, that's exactly what happens. So as the expected ZVS boundary increases, we see the dark red region grow as well, as expected. All right. And then finally, just talk for a moment about our next steps. So we've done, as I've shown you, a lot of analysis on this topology and tried to understand what the knobs do within the design space, what the different design parameters do, and how that influences the system efficiency and performance. And what we've concluded is that this topology is too complex to be able to optimize by hand. And so what we're doing now is we're implementing a genetic algorithm approach to select overall optimized system parameters. For our initial study that we just completed, we're looking at the following system parameters, which is the number of parallel MOSFETs, dead time selection, resonant inductor. Then we have a couple of different candidate MOSFETs, and we're looking at things like maximizing efficiency and minimizing volume. As part of this effort, we're leveraging Purdue's genetic algorithm implementation called GoSet. Many of you may be familiar with that, which is an open source tool that is really easy to use. So a quick look at our genetic algorithm setup. So the initial study that we performed is focused on minimizing the overall MOSFET losses. We're using some sub-procedures from a really nice paper that was recently published. This is out of Professor Kohler's lab. This is a TPEL article, April 2019, that detailed a method to estimate different loss mechanisms of semiconductors from datasheet values. So we're leveraging some of those equations that were in that paper, but very importantly, we need to know if a given set of parameters is expected to yield ZVS or not. So for that step, we're utilizing our theoretical model that I presented earlier. So we have estimate of the kind of 4 contributors here: our conduction losses, our turn-on switching losses, our turn-off switching losses, and then COS charging discharging losses, which we just use a estimate of 20% of the energy stored in the output capacitance. And so in this particular example, again, this is a preliminary study where we fed all this into GoSet. And in this preliminary case, we wanted to minimize the overall MOSFET losses. So we looked at trading off between conduction and switching losses for this particular configuration. And some results from GoSet, we're looking at different resonant inductor values, different dead times, and how many MOSFETs to put in parallel, and then the different MOSFET candidates that we had in the mix there. And then one interesting thing is that the genetic algorithm kind of settled on an optimal dead time of about 150 nanoseconds for the lagging switches. So out of this, we developed a Pareto front that came out of this for our solution space. Again, this preliminary study looked at trading off conduction and switching losses, and we see that we have 2 candidate configurations that dominated over all the others of these red circles here. And so we are continuing to advance this optimization process. The next step is to introduce the losses from the other components within the system, the output filter, secondary rectifiers, Semiconductor, and so forth, such that we can do an overall Pareto optimal analysis between, for example, volume and efficiency. But that work is ongoing. All right, so in conclusion, just wanted to kind of highlight a couple of things. I've tried to make a case that soft switching techniques are critical if you want to simultaneously achieve high efficiency and high power density. However, the mechanisms that underlie these methods, such as ZBS, are relatively complex. And by that I mean they depend on many system parameters. Some of the system parameters that are important for determining whether or not soft switching is achieved include the semiconductor device parameters themselves, particularly the intrinsic capacitance of the devices. So historically, a lot of times bench level tuning has been used kind of to optimize converters on the bench, and I would argue that that's rather an inefficient means. There's a typo there that should say is an inefficient means for achieving optimized converter operation. And I would submit to you that a much better solution is to utilize an optimization algorithm, which, however, requires that you have a sufficiently detailed converter model that not only can represent the loss mechanisms in the system, but also is able to discriminate whether or not a given configuration will achieve soft switching. And I've presented an example, one example of such a model here today for the phase shifted full bridge, and hopefully this is a concept that could be extended to cover other topologies as well. But with that, I would like to conclude my talk, and I'm happy to take any questions. Thank you.
Thanks, Andy. That was excellent. Really good technical presentation and good slide materials to follow along with. So I really appreciate it. We have plenty of time for Q&A, and because of the large number of folks on the line, I would ask that you go to the top of your screen, and there should be a drop-down menu in the WebEx toolbar for chat, and type your question into the chat window, and I'll ask them orally, and then Andy will answer them. We have a half dozen questions already, Andy, so I'm going to go ahead and start. First question is, it's interesting to hear that soft switching is not achieved at just the design stage, but rather that one must build a prototype and then test. I've been misled by many designers in the past telling me that everything we do here, insert big company name, is soft switching. Not exactly a question, but do you have any response to that comment?
Yeah, I do. That's a great comment. So what I would say is there are well-known rules of thumb that can be used to kind of design a system that will work well and that will achieve ZBS across a broad range of operating conditions. And if I jump back here to some of the model predictions, one of the things that I didn't really spend any time on, but I should point out, is that our model also kind of takes into account some of these rules of thumb. So here I'm showing if you really wanted to optimize this converter, what you would do is you would select a dynamic dead time that kind of follows the bottom of this curve, and that would give you a measure of independence from the parameter value that I'm studying here, which is the resonant inductor value, and it would also minimize the amount of dead time which is, it's undesirable to have a very large dead time, because that's time during which you can't transfer power to the load. So, a way to do kind of a design optimization would be to follow the bottom contour here. However, that's a pretty complex controller design. So what many designers do is they kind of select an optimum fixed dead time, which there's a rule of thumb that's commonly used that says 1/4 of the resonant period is a good fixed dead time to utilize. And what I'm showing here is that value will actually do a reasonably good job in most cases. And so what I would say is that, following kind of conventional rules of thumb will produce a reasonably designed converter. However, I would argue that it would not be an optimal design. Because again, in my experience, a lot of this has to be done on the bench after your prototype is built, because there's certain parasitics that play a role in determining whether or not ZVS is achieved. For example, the leakage inductance of your transformer, which you may not know during design time, and you won't fully know how all of the pieces will work together until you get it on the bench and operate it. So I would say, yeah, there's kind of two things. One is you kind of use your best, the best knowledge that you have during design time, but then conventionally you kind of do that last mile tuning on the bench. And what I'm proposing here is that if we have a sufficiently detailed model, we can kind of push more of that tuning into the design space rather than at the bench level when we have a prototype built. So hopefully that helps.
Thanks. We have lots more questions to go. The next one is, what is the key difference between DAB and PSFB?
Yeah, that's pretty easy one. The main difference is phase shifted full bridge is a unidirectional power flow. So it's strictly from primary to secondary. A dual active bridge where you have a full bridge on the secondary side as well. Let me jump back to my schematic. Yeah. So in this case, for a DAB, we would have a full bridge over here as well. And DAB, the advantage there is that we can do bidirectional power flow. That's my understanding of the primary difference between the two topologies.
Okay, next question is, with a large LR, we have a large duty cycle loss, which influences the operating range. How do you do that trade-off?
That's absolutely correct. So one of the things that that we saw when we looked at the model prediction is that the large LR range, as I described previously, gives you a very generous window to select the switching time. However, it does have the major negative consequence that that limits the slew rate during the transitions, and specifically the primary current. The DIDT is kind of governed by the size of that resonant inductor. So that means you can only, that results, so to the questioner's point, a large resonant inductor means you can only transfer power across the transformer during a subset of the switching period, which is commonly called duty cycle loss. So that's a tough one, because you kind of have to trade off your efficiency versus the power that you need to supply to the load. So as I also showed in the efficiency map, a large resonant inductor also achieves higher efficiency across a broader load range. So I don't really have a good quantitative answer for you, but if we look at our efficiency maps, which I'll jump ahead to here, one of the things that we saw when we did these sweeps is that using a larger resonant inductor allows you to get very high efficiency down to very light load. And so perhaps one way to manage that trade-off is to understand whether light load efficiency is important to your application or not. And if it is, then a large resonant inductor is a good decision. If it's not, and if you prioritize just the heavy load efficiency, then a smaller resonant inductor can get you heavy load efficiency without incurring as much duty cycle loss.
Okay, thank you. The next question is, I hope I'm saying this right, the C sub OSS for silicon power MOSFET varies by more than an order of magnitude with drain bias. How do you determine C sub OSS EQ?
That's a great question. So the details for that are in the paper that I referenced. But essentially, we look at it at the drain to source bias that we're operating at. So it's clear that COSS is a strong nonlinear function drain to source bias. And so what we're doing is we're looking at the we are considering that, and we're looking at the COSS at the DC link value that we're using.
Okay, next question. What is the short circuit capability requirement for the silicon carbide power MOSFET in your case?
That's a great question. Short circuit withstand. So we didn't really, as part of this effort, we didn't really do short circuit withstand testing. I would mention that this controller does implement cycle-by-cycle current limiting. So it has peak current mode control as well as cycle-by-cycle current limiting. So and at 100 kilohertz, you know, we have a 10 microsecond switching period, and the reaction time of the controller is pretty quick. You know, sub microsecond level. So I would say, you know, as far as short circuit withstand time, a microsecond would probably be sufficient for this particular case. However, the caveat is we are doing cycle-by-cycle current limiting.
Okay, next question. Why not use LLC? It should be more efficient.
That's a very good question. I had a slide which I actually hid because I was worried I would run out of time. Let me see if I can just go back to it real quick. That talked about that very thing. Okay. All right. So this, let me unhide this slide. So of course, the two dominant topologies for soft switching are PSFP and fully. So we think of PSFP as a pseudo-resonant converter, and the major competitor is the fully resonant LLC converter. In my case, we had down selected between these two topologies to the PSFP, mainly because it's a fixed frequency converter. So the LLC, if you're not familiar, it has a dynamic switching frequency that is utilized to kind of track the resonant behavior across power levels. So you kind of dynamically scale the switching period to achieve resonant switching transitions as the load changes, which can create some challenges, for example, with a design of your EMI filter, because you can't just simply notch out the region around your switching frequency and dominant harmonics. You have to account for the fact that the switching frequency is actually moving around. That's not to say it's an untenable solution. There are very many very high performance implementations that have gotten around that challenge. But for our case, we were actually looking at data center applications, and the PSFP, from my understanding of talking to folks in that industry, is currently the dominant topology that's used in data center DC to DC conversion. So for that reason, we stuck with the phase-shifted full bridge.
Do you hear me? Okay. Why did you not consider modifications to the basic topology for extending the ZVS range?
That's a great question. So there are, for those of you familiar with this topology, there are numerous variations found in the literature of auxiliary circuits that can extend ZVS down to lighter, light loads, and there are, numerous examples of kind of modifications and variations on the theme of this central kind of basic topology. However, in our case, our objective was to create a theoretical model that would allow us to predict when ZVS occurred and then validate that model. And so we wanted to utilize kind of the standard topology of this converter rather than one specific kind of variation. So it was more about how can we design and implement and validate a theoretical model that can then be used to optimize. So it wasn't about necessarily getting the highest possible achieved efficiency. It was how can we create a model that will give us new knowledge about how we can then optimize this fundamental topology.
Okay, next one. I just want to clarify that the soft switching in your setup is limited to ZVS turn on, and the turn offs are still hard switched. Is that correct?
That is correct. So the ZVS topology, or the PSFP topology rather, does achieve ZVS at turn on. However, the turn on losses are the dominant source. There's a really nice paper from Infineon, I think it's from Infineon, called Mastering the Art of Quickness, that talks about turn on versus turn off losses. And there are a few criteria that you can utilize to make sure that the turn-off losses are small. And this particular paper calls it quasi-ZVS at turn-off. And the main criteria are that you have a sufficiently fast gate drive and a sufficiently high value of intrinsic capacitance. And if those two conditions are met, then the turn-off losses are essentially negligible in comparison to the turn-on losses. So that is often the case, and is certainly the case in this particular converter. So it turns out that really if you minimize the turn-on losses and you pay attention to a few guidelines, essentially for all intents and purposes, that can eliminate all of your switching losses.
Okay, next question. What method did you use to measure the voltage accurately?
So for the voltage measurement, I'm presuming we're talking about during the efficiency captures. That was done with the power quality analyzer. So I can jump ahead here. Since what we're doing is measuring essentially a DC quantity, so here, this is a snapshot of the back of the PQA. So we just have a V high and V low for each channel. So one of these was attached to the input, one to the output. And we found that the sensitivity of those measurements was not very high with respect to determining the efficiency accurately. So essentially, those are really basically DC quantities. We do have some ripple on the output. The input is a pretty clean DC rail, but that's how we did it. We used our PQA inputs, and there is averaging applied within the PQA software that does minimize the influence of the ripple on the input and output. And we experimented with different values of those, but did not find them to be overly sensitive in determining efficiency, unlike the current. The current was really the main sensitivity there. Okay,
next question. Is there any control difference between DAB and phase shift?
That's a great question. I'm not an expert on DAB, and I really just don't have a good answer for that.
Okay, next one. Actually, the LLC gives better EMI, as the pure sine gives you much less harmonics. I guess that's a comment, not a question.
Yeah, I would say from my research, I've found that the main those advocating for LLC typically are advocating higher efficiency. And from our literature studies, we found that commonly LLC is able to push to higher efficiency than PSFB. But again, you got that dynamic switching frequency to deal with, which again is not an insurmountable hurdle, but it does, from what I understand, complicate the filter design. So I'm not here to advocate for one over the other, just we chose the PSFB as our example and developed a model for it. I would say one of the, in the future work category would be doing the same kind of thing for the LLC topology, which I see as a very advantageous and a very desirable topology in its own right.
Okay, can you talk a little bit more about the HF transformer design?
I can a little bit. All right, let me go back to the picture of it. So again, we outsourced the transformer design to Peyton Planer. We actually did several, I didn't include any slides to show this, but we did a couple of internal design transformers before we contacted Peyton for help. And essentially, some of the challenges that we met in the first couple of iterations of this converter, the high-frequency transformer was the major bottleneck. We had thermal runaway with the core of our prototype transformer. One of the major challenges that we had was proximity effect in the windings at these high frequencies. The DC resistance of the winding was rather small in comparison to the AC resistance at 100 kilohertz, and in particular the current crowding that we saw at high frequency in between the primary and secondary windings was such that the windings would get very, very hot and then heat up the core, and then the core would begin to saturate. So after having done a couple of iterations of designs ourselves, which we had done with PCB windings, and we had gotten the thickest, I think we did like 6 or 8 mil copper on a very, very thin substrate, and we had many, like I think 20 to 25 stacks of windings inside the core aperture, and we simply couldn't make it thermally stable at 10 kilowatts. So we contacted Peyton Planer, with some of my collaborators at other institutions that had good results working with Peyton, and they cut windings out of foil using a wire EEM process. So we got much better connectivity of the primary and secondary windings, and that's the design that I'm showing here on this slide. Essentially, they used the same core that we had been using, but their winding design is much superior to the original one that we had, and so that resulted in a reduction in AC resistance, which then minimized the heating of the windings, which then minimized the heating of the core, which resolved our thermal runaway issue that we initially were dealing with.
Okay, why, let's just a second. Okay, why does the efficiency go up as temperature rises?
That is a great question. That's something we've been puzzling over. So let me go back to this. So the question is, why doesn't the efficiency go down as things warm up? So this is something that we've been puzzling over ourselves, because my expectation, like this questioner, is that as things heat up, RDS on is going up. For the switches, the conductivity of the various conductor structures should be going down. So I would actually expect efficiency to drop over time as things are warming up. However, the trend that we see is the opposite. The only plausible explanation that I have right now is that it could be that also we're seeing some thermal dependence on the shunts themselves, that the shunts are warming up, and therefore, the voltage across the shunt is increasing as a function of time as things stabilize. So I don't have a good answer for you. I have kind of a hypothesis, but that is actually something that we're studying right now, is to try to get to the bottom of that. But the main thing I wanted to point out is that you shouldn't just take a one-shot efficiency measurement and call it a day. You should actually track it over time and do some averaging so that you get a much better and more accurate estimate of efficiency.
Okay. The next comment is, ZVS circuits typically need to be kick-started. Again, just a comment. Yeah. We're about to wrap up, so in the last few minutes, if there's someone who claims that their question is too complex to type it, if you want to speak out orally, I think we can do that, because some people have logged off. Did you have a response to that comment before people jump in with questions, Andy?
Not really. I don't really understand that comment, actually.
Okay. Yeah, the last few are, again, more comments. So if anyone wants to ask any questions orally before we wrap up, just unmute yourself and jump right in.
Yeah, hello, this is Bruce Karsten here. Am I online?
Hey, Bruce.
Hey, Bruce.
Yes.
Yeah, some of these comments were mine. As I mentioned here in the next comment, I was involved in a 1 kilowatt, 1 megahertz converter, phase shifted bridge converter design in the 86 to 88 time frame, and we faced a lot of these problems and managed to solve them out there. Just to sort of quickly kind of, the kickstarting is due to the fact that if you consider that if you gradually raise the input voltage on a circuit, typically you're going to have voltage on all of the switches, and if you don't force at least one of them to turn on to get the thing started, the voltage will not drop to 0 on any of the other switches. Nothing ever happens. So typically we would have an allowed maximum dead time and then force the switch to turn on for hard switching. But as I said, I'll cover a lot of the others verbally since they'll be a bit faster. We solved the optimum duty cycle problem, as I said, with having a maximum dead time, but we also sensed the VDT across the device, and when the voltage ceased to fall, we automatically turned it on. Typically, ideally, that was when the voltage had gone to 0 and the device began to reverse conduct momentarily. But even at light loads, it would force it to turn on. However, we later developed circuits, probably some of which have been later published, so that we were able to achieve 0 voltage switching down to no load, which was absolutely essential, but when we were switching at a megahertz with silicon switches. So anyway, that pretty well other comments, we also found the phase-shifted bridge, and by the way, we used initially we used the leakage and magnetizing inductances of the transformer for the resonant inductor, but we found one of the problems we found is that it was not good for operation over a wide input-output voltage ratio. The RMS currents tend to get quite high under extreme ratios. And we also found that the transfer function was not linear, but involved square law terms.
Okay, so, Bruce, we're going to have to wrap up in a minute, please. So please conclude your comments.
They're finished.
So, Bruce, thanks for those comments. Just one kind of quick response with regard to kind of the kick-starting. I do recognize now, I understand what you mean. In our implementation, what we do is we have a soft start implementation. So we ramp in the voltage reference over the first 10 or 20 milliseconds of operation, and just we take the hit at startup where we're doing some hard switching during the first few hundred cycles until things get going. So I didn't realize the question was about soft starting or about the startup conditions, but that's a very good point. And again, you know, of course, as I mentioned, there are plenty of auxiliary circuits in the literature that define how to kind of squeeze the last few percent of efficiency out of this topology, but our goal during this effort was to develop a model that could then be used in an optimization loop. So kind of we set aside some of those auxiliary opportunities to focus on kind of the core of the topology.
One more comment. This is in regarding to the efficiency kind of flattening, not going down. Maybe the reason is because the output diode, as they warm up, more efficient, and that's a typical thing when you use diode for output. And if you would use sync ref, which is a problem because of the high voltage, then it would be the other way around. But I think it's a simple explanation.
Yeah, that's a good point. And in the redesign, we have synchronous rectification on the output, so that'll be a very good comparison. Once we have the new version implemented, we can do a comparison and see if we get the opposite trend. But thank you for that. Thank you for that comment.
Yeah, kind of simple. And also, if you would use LLC, probably you would have 98, between 98 to 99. So in the next go around, when you use LLC, you probably should use that topology. The frequency range variation is not much. It's like maybe 2.5 to 1, 3 to 1.
Yeah.
And since your switching frequency can be a lot higher because you don't have both voltage turn on and turn off losses, you will have a pleasant surprise.
Yeah, great comment. And again, I'm not advocating for one topology over the other. This is the example that we selected for this model, but clearly in future work, the one very promising idea is to do the same type of model for LLC. So we all agree that that's a very useful and important topology as well.
Yeah. When you visit us at El Segundo, I think we saw you one time, is Moshe. We'll be glad to have a more lengthy chat.
Great. Thank you very much.
Yeah.
All right. Well, thank you all for joining us today, and thanks in particular to Andy Lemmon for taking so much time to prepare and for sticking around and answering all the extra questions that we got today. We really had a lot of participation, and we really appreciate your time and effort.
Absolutely. Thank you for the opportunity.
Bye. And
we hope to see you all again in November, November 6th with the Naval Research Laboratory. So have a wonderful day. Bye-bye.